Most mariners are well aware of the hazards posed by conventional electrical equipment. But there is another form of electricity that can be as dangerous. Static electricity and stray currents exist all around us. They are hazardous and need to be carefully managed. If not, in certain conditions, they may trigger a lethal explosion. Static electricity and stray currents are quite different in nature. Static electricity usually involves low currents, typically measured in milliamperes, and extremely high voltages. Here, the plate is charged to about 50,000 volts. If this accumulated voltage discharges across an air gap, it creates a spark powerful enough to ignite hydrocarbon vapors. Stray currents usually involve high currents, but at voltages that are comparatively very low. If such a circuit is broken, there is a contact discharge. With sufficient energy, this can form a bridge of molten metal between the electrodes and is commonly called an incendive arc. For an explosion to occur, three elements must be present: fuel in the form of hydrocarbon vapor, or fine particles such as coal or grain dust, oxygen from the air, and an ignition source such as a spark or an arc. Both static electricity and stray currents can supply this ignition source. So, despite their differences, they both pose a similar risk to vessels, especially those loading, carrying or discharging volatile cargoes where hydrocarbon vapor and air are both present. Static electricity is a natural phenomenon. It is a hazard and must be carefully managed. An electrostatic hazard requires three elements: charge generation, charge accumulation, and electrostatic discharge. As the meter shows, friction between two dissimilar substances can cause charge separation to occur. This can be demonstrated by rubbing a glass rod with a synthetic material, like nylon. In doing so, atoms that were neutral now become positively charged if they lose an electron, or negatively charged if they gain an electron. Charged atoms or molecules are usually known as ions. In a pipeline, product flow also dislodges electrons from the atoms, allowing them to migrate from one material to the other. If the two charged surfaces suddenly become separated, then a large voltage difference can develop, and the risk of an electrostatic discharge is greatly increased. This may occur during many tanker operations. For instance, the flow of liquids or droplets through a pipe or a filter, where bends and constrictions will increase the generation of static charges. The forceful ejection of particles from a nozzle, the agitation of a liquid against a solid surface, or the rubbing together and separation of some polymers. The positive and negatively charged atoms try to recombine to neutralize each other, or flow to earth or ground. But if the material is a poor conductor, they are trapped, or flow very slowly, and the charge accumulates. When the voltage is great enough to jump the gap between 2 points, an electrostatic discharge results. If sufficient energy is released, in the form of a spark, as shown here, then it will ignite the hydrocarbon vapor. Electrostatic hazards are well known. They can be minimized by strictly following the operational guidelines jointly recommended by owners and oil companies. It is common sense that no tanker operation that may result in the release of hydrocarbon vapors should take place when there is an electrical storm present or nearby. It is just as vital to manage the static charges that can build up during loading and discharging, tank washing, or steam cleaning. As a general rule, all metal objects should be electrically bonded together with a direct path to earth. So, for instance, when tank cleaning, portable cleaning equipment and steam hoses must be bonded to the ship's structure. When dipping tanks or taking hydrocarbon samples, always ensure that all metallic components are continuously bonded and grounded to the ship before they're introduced into a tank. An unearthed conductor could spell disaster. If ever static accumulator oils are loaded without the ullage space being inerted, no dipping, ullaging or sampling should be undertaken until at least 30 minutes after the completion of loading. Always ensure that the ISCOT recommendations are followed. Man-made materials, like polypropylene rope, can generate a significant static charge, as the graphical display indicates. So always use natural fibre ropes for dipping, sampling or checking oil ullages. Some shipping companies now issue anti-static footwear. As well as providing protection against mains voltages, they also prevent electrostatic buildup. It is strongly recommended that anyone entering or working in an area where flammable vapours might be present should wear approved anti-static footwear. The shoes have a resistance of around 1 megohm. Most hydrocarbons ignite easily, so loading and unloading hydrocarbon operations pose special risks. The flow of product through the pipes and loading arms can create very high electrostatic charges. Hydrocarbons vary in their ability to accumulate static electricity. Black oils, such as asphalts, crude oil and residual fuel oils, are good conductors, so charges don't build up, and they can usually be loaded with minimal anti-static precautions. Distillates, like gasoline, kerosene, jet fuels, naphtha, and heavy gas oil, in general have a much lower conductivity. They are classified as static accumulators, for which special precautions are needed. Even black oils containing water will still generate high voltages. This is because the presence of water or other contaminants within the fuel may increase the charge levels. Deciding what electrostatic precautions are necessary depends on a number of factors. First, check whether the oil has a low conductivity and is a static accumulator oil. Secondly, think about the volatility of the cargo, that is to say, its explosive nature. This can vary dramatically. It can change, especially if a non-volatile static accumulator oil is handled at temperatures around or higher than its flash point. Thirdly, consider the tank atmosphere, especially if the tank has not been inerted. Most hydrocarbons are flammable in concentrations of between 1 to 13% in air, especially if the tank has not been inerted. Static accumulator oils must be loaded with caution. During the initial loading phase, the velocity in the pipeline should not exceed 1 meter per second. Then the rates may be increased. Make sure you follow your own company's specific recommendations. By reducing the flow, less charge is generated in the first place. A lower flow rate also reduces splashing and surface turbulence, which will help limit the static buildup. During loading, and for 30 minutes after completion, no metallic dipping, ullaging or sampling equipment should be used unless the ullage space is protected by inert gas. On all oil and gas tankers, there are specific zones of danger. Nonetheless, when berthed at a refinery, areas that are classed as safe at sea may be part of a hazardous region in port. This will affect how some jobs are carried out and may require additional precautions, such as a ban on welding. Another source of concern are helicopters, which develop a very substantial static charge when in flight. Therefore, no helicopter operations are normally permitted over the tank deck whilst any loading, discharge, tank cleaning or gas freeing activity is in progress. When winching or delivering underslung loads, no one on deck should touch the cable or load until the static has been discharged. Failure to do so could result in a severe shock, at the very least. On many vessels, an inert gas is used to replace air in the tank or ullage space. Without the inert gas, air may enter the tank and form a potentially explosive mixture. If the inert gas system should fail during discharge, all operations must be stopped. If carbon dioxide is injected under pressure, it can generate high levels of static electricity. So the CO2 system should only be used for firefighting. Attempting to inert a pump room that might have a flammable atmosphere because of a fire in the next compartment could cause an explosion. Stray currents can be generated by cathodic protection systems and by potential differences between ship and shore. They must not be confused with static electricity. However, stray currents may also cause incendive arcing, so the dangers must not be overlooked. In the past, it was common practice to connect the ship to the jetty with a bonding wire. However, the bonding wire does not act as an electrostatic discharge path. The aim was to override both the ship and jetty cathodic protection systems so as to maintain the vessel and the jetty at the same electrical potential. Because the currents are very large and the resistance of the wire is not sufficiently small, the bonding wire cannot carry out this function effectively. The International Maritime Organization actively discourages the use of bonding wires and recommends phasing out their use. To prevent arcing, best practice recommends the use of an insulating flange or a single length of non-conducting hose between ship and shore. The insulating flange should have a minimum resistance of 1000 ohms to be effective. All other metal on the jetty side and the seaward side must be electrically continuous and bonded to ground. This deliberate discontinuity, provided by the insulating flange, is the most effective way to avoid the accidental discharge of stray currents in hazardous areas. It will work even if the flange is iced over. Although ice is a conductor of electricity, it still provides sufficient resistance to low voltages, such as those generated by cathodic protection systems. Electric welding presents many well-known hazards. In some cases, the dangers have been made worse by using the hull as a return. It means you only run out one cable. But in doing so, you greatly increase the risk of an accidental arc that could ignite any hydrocarbon gases. This practice is fundamentally wrong and should never be allowed on board ship. there has been some concern that radar equipment can induce dangerously high stray currents in metal structures. As a general rule, a properly sighted and maintained radar scanner presents no ignition hazard on board ship or on the jetty. With smaller ships, where radar scanners may be close to jetty structures, then some hazard may exist. The tanker industry operates to the most stringent safety standards. But there is always the potential for an accident to happen, especially where electrostatic charges and stray currents are allowed to develop. Working with highly volatile cargoes demands the highest levels of professionalism. Taking a shortcut, improvising with the wrong equipment, or ignoring agreed procedures could result in a devastating explosion, serious injuries, and loss of life. Static electricity and stray currents are an ever-present danger to you, your vessel, and all the people who work on her. By taking appropriate precautions and following the approved procedures, you can minimize the risks to yourself and to all those around you. For further information, please consult the booklet that accompanies this video.